All right. So again, good morning, everyone. Today is going to be a very short meeting, maybe 10-15 minutes at the most. We're going to discuss the exam review for exam two. Exam two will be on Wednesday, uh, on Thursday, sorry, it's on Thursday, and that will be April 1st. And the exam will cover chapters 5, 6, and 7. The style of the exam is going to be similar to the first one. We're going to have multiple conceptual questions, such as define this for me, or some acronyms to define, or what's the difference between this and that. And then we're going to have multiple calculation questions. So this is just, again, in a nutshell. You don't need to have anything besides uh, a pen or a pencil and a simple calculator. That's all what you need. Uh, all the tables and figures and um, equations, they will be at the back end of the exam itself. So again, don't be fooled if you see the exam is like 15 pages. The exam itself is maybe 4 or 5 pages, and the rest are all the equations, figures, tables that you may need. But again, you need to be familiar with those tables in order for you to distinguish which table or which figure you need to use. Any questions before I just go through the slides and just give you an idea?
Yes, will this like be recorded and posted?
Yes, I will post this in couple hours at the most.
Oh, okay, thank you.
Thank you.
Hey, are we waiting in the same place as last time?
Yes, we are going to be meeting at the two rooms, at the two labs, the environmental lab as well as the soil slash pavement lab. Yeah.
All right.
Any other questions? All right, so let me go through and share here with you the slides, one lecture at a time. All right, so this is here chapter 5. Again, when the exam will be chapters 5, 6, and 7. Chapter 5 was a short one, and I'm expecting you here to do some to understand some definitions. What are the major traffic stream parameters that we've gone by? What's the difference between uninterrupted and interrupted flow? Simple, probable question. If I ask you what are the define for, or list for me the three main variables that actually form our understanding of any traffic analysis. Those are flow, density, as well as speed. Simple equation like this, I will not be providing in the exam. Those are again very conceptual questions. So this is the flow. The flow is basically number of vehicles over a certain period of time. So that equation in particular, it will not be provided in the exam. But then the derivation all the way um, to reaching again such equations like this here, those will be provided. So the Q, the flow is basically the reciprocal of the average headway. And then we went through the speed. I can ask you what's the difference between the time mean speed and the space mean speed. The equations will be provided to you uh, for both methods. Like for example, this again we've gone through a derivation, but this is really the equation that we ended up using, so it will be provided to you if you need it. Now we move to the density. This is the same thing. This is a very conceptual equation. Density is number of vehicles over certain length of a section. So that will need to be remembered. But the derivation of the equation all the way to the last equation, which is again the density is the reciprocal of the average spacing, that will be that will be provided to you. I can also, this is very classical question. Give me or provide for me, please, the 2 or 3 microscopic measures versus 2 or 3 macroscopic measures. Excuse me. So, or I can ask you, what's the difference conceptually? What's the difference between a microscopic and macroscopic parameters? So the macroscopic basically measure the individual relationship between pairs of vehicles within a certain traffic stream, versus the macroscopic is actually give us an understanding of the characteristics of the traffic stream as a whole piece. This equation also you need to know Q is equal to U times K. So the flow is equal to the density times the speed. And most importantly, actually, you need to draw, you need to know what's the relationship between each one of the 3 parameters. And, or if I can give you the picture, you need to explain it to me, or both. So, for example, if I tell you how would a relationship look like between the speed and the density, you should be able to draw this relationship and also explain it, especially defining the extreme points. What's this here? Why when density is 0, I have the highest speed? Why when I have the jam density, the speed is 0? Those are the things. I'm not expecting you to know the equation. If the equation here, well, if you need to use the equation, it will be provided to you. But most importantly is really again the relationship between the 3 parameters. Same thing here. I can ask you draw for me the relationship between density and flow. So you should be able to draw the relationship, and also you need to explain why these 3 points here are happening this way. When there is no density, there is no flow. When there is jam density, there is also no flow. But when we reach the cap density, this is the cap flow. All the way to the third relationship, which is what's the relationship between speed and flow. So you should be also able to draw that relationship and explain the three different points defining this relationship. Again, the equations will be provided. Don't worry about the equations, but you should be able to understand the relationship between. Really, again, this is a summary of the entire chapter. The 3 relationships and the 3 factors and their relationships, and how can you draw them, and how can you explain why do we have again why this line goes downwards, why do we have a curve like a peak here and then it goes down. Same thing for the flow versus the speed. So from this chapter, honestly, there might not be many calculations, but lots of conceptual questions that I'm intending to test you on this chapter. Any questions on chapter 5?
Um,
Yes, please.
all of the equations on this chapter are provided.
Yes, the equation, as I said, the equations like this, it will be provided. Equation like that also will be provided. But something like this is a very conceptual equation. If we do not understand that Q is equal to U times K, we're missing the point. So this equation has to be remembered. Same thing for this density is number of vehicles over certain length,
Okay.
as well as this equation. Q is equal N over T. Flow is number of vehicles per time. So those are really again just the 4 equations. So the 3 equations, one for the speed, one for the density, one for the flow, as well as this equation. So really 4 of them, just 4. Anything else, it will be provided in the exam.
All right, thank you.
You're welcome. Any other questions for chapter 5? All right, moving on to chapter 6. Chapter 6, it has lots of calculations, and you should expect to see again many, at least couple of computation questions, as well as maybe theoretical questions. In chapter 6, we did discuss um, the concept of the level of service for three different structures or facilities. So the first one was the level of service for freeways. So we need to we define what is a freeway. I can ask you what's the difference between a freeway and a highway. That's a conceptual question. And how would you define a freeway? Those are again some of the characteristics of a freeway. I can ask you, or I can give you this picture here, and I tell you, define for me what are the three major segments of any freeways. So basically, it's the basic freeway segment, the weaving areas, as well as the merging and diverging areas. Or I can ask you a simple question. Which section or which piece of those three pieces here we use to calculate the level of service? And the answer is it's the basic freeway segment. That's another conceptual question that can be asked. What are basic freeway segments typically characterized by three main measures? What are they? Basically, the density, the speed, as well as the volume to capacity ratio. Again, when I'm skipping something, that doesn't mean it's not important, but I'm just trying to remember off of my memory again, based on the exam that I wrote a couple days ago. But everything is important. But like here, for example, this is a good table that will be provided to you probably, and you can use it to get the level of service based on the density value. I can ask you, give me, maybe I'm not going to ask you for calculation, but although I will, but also what are the procedures to get the level of service? You need first to establish what's the base conditions. You need to estimate or calculate or measure the free flow speed to get the analysis flow rate, and then calculate the service measures to determine the level of service. I also can ask you simply, give me two or three or four ideal or base conditions for freeways. You should be able to remember these. Excuse me. So again, you should be able to remember what are the base conditions for freeways. And then here to the calculations. This equation, this is very empirical equation. It will be definitely provided to you in the exam. How to estimate the free flow speed. 75.4 minus FLW minus FLC minus 3.22 TRD to the power 0.84. The trick again in this chapter really is to familiarize yourself with the tables, which tables work for what facility. There are tables only for freeways, there are tables only for highways, and there are tables for only two-lane highway, but also there are tables that they are shared among two or three different of these facilities. So for example, this table here is FLC, this is FLW. It has to do with the correction for the lane width. This here, table 6.4, it will be for the lateral clearance. And then TRD. This equation is not going to be provided. This is by definition. This is the total ramp density. I'm going to give you the number of ramps. You're going to divide it by 6. This is how to get TRD. This equation will be provided to you in the exam. VP, in case if you need it. So VP, this is how can we get the analysis flow rate. Or to be more accurate, this is the 15-minute passenger car equivalent flow rate. But the peak hour factor, this is a very conceptual equation, and I'm expecting you to remember it. We explained it, it's simple. This is again total volume over the worst 15-minute flow times 4. This is how you get the peak hour factor. The peak hour factor has a minimum value, possible value of 0.25, which is really bad. That means all the bad traffic that happens in the peak hour happens in 15 minutes only, or it can be as good as 1.0. And that would be the best case scenario, meaning that although I have a bad hour, but that bad hour actually the amount of traffic in that peak hour is uniformly distributed within the quarters of that hour. FHV, this is the heavy vehicle adjustment factor. That will be also provided to you to get the heavy vehicle adjustment factor. But the ET and ER, those are the tables. As I'm mentioning here, table 6.5, table 6.6 to get ET and ER. This is the table that we used heavily. 6.5 ET and ER. If I don't tell you any grades, what was the specific grade on the facility, I'm just gonna tell you it's a level or rolling or mountain terrain. This is how we're gonna pick ET and ER. But if I give you a specific upgrade or grade, like less than 2 or 2 to 3 or 5%, which is B somewhere between here and here. This is now, we need to know what's the percentage of trucks to pick the exact ET. And for this table, you're going to pick the exact ER. But if I'm not giving you the what's the exact grade of that facility, you're just going to use this simple table, table 6.5. Same thing here, this is table 6.8 for trucks and buses for specific downgrades instead of upgrades. So again, depending on the question. FP, as we said, it's going to be ranging from 1 to 0.85. If I don't tell you anything about this freeway, or if I tell you that the majority of the people who are using the freeway are typical commuters, we're going to assume that FP is 1.0. If not, I will be giving you the exact FP to use. But if I'm not mentioning there is no FP in the equation, don't ask me what is the FP. FP is 1.0. This is the default value unless mentioned otherwise. Then this is the same equation that we used in chapter 5. So I'm not going to give that to you. If you get the VP and if you get S, which is the FFS, the free flow speed, you divide the two to get the density. Once you get the density, you can go now to this table right here, to this graph, very famous. And honestly, you will be using it in the exam. I'll just be blunt here. So I need to test you how to use this table. So the flow rate, you can go to the flow rate and then connect it to the free flow speed, and you're going to be able to get what's the level of service for this facility. Or you can use the table. I highly recommend you to use the graph. It's much easier. That's just the level of service for the freeways. The second lecture for chapter 6 was for level of service for for multi-lane highways. So this is multi-lane highway and level of service analysis. It was a short part of the chapter because it's very similar to freeways, but there are also some differences that we've drawn. I can ask you, what are some of the key characteristics of of multi-lane highways? I still cannot call it a freeway, but what would be some characteristics of multi-lane highways? I gave you multiple of those, and you should be able to discuss or list 2 or 3 of these characteristics. These are some of the key factors distinguish a multi-lane highway from a freeway. There's even a bigger list here of things that can differentiate between a highway and a freeway. The procedure is the same. I can ask what are some of the base conditions for multi-lane highways, which are a little bit different, yet they are similar in a way to freeways. This equation will be provided to you in the exam in case you need it. This is the equation to estimate the free flow speed for multi-lane highways. There are some tables here specifically designed for multi-lane highways, but some of them are shared between multi-lane highways and freeways. For example, FLW, as you could notice here, it's the same table, same table 6.3, same table as used for freeways. FLC is different though. FLC lateral clearance, now we're using table 611, which is very unique to multi-lane highways, way different than freeways. Table 612, that was a new one also for undivided highways versus divided highways, whether we have a median or not. That was not even the case for freeways. For freeways, there is always a division. There's always a wide median. access points, same thing. It was a new table for multi-lane highways. And then we arrive at the same equation, VP, to get the minimum, 15 minimum, 15 minutes passenger car equivalent flow rate, which is the same. That's why I say it's the same procedure. And then you arrive at similar figure, but not exactly the same. And that's why, please make sure you're using the right figure. If I'm giving you a question for multi-lane highways, that's the figure. If I'm giving you a question for a freeway, it's the previous figure. So make sure that you're using the right figure. But the concept is the same. You're gonna get the flow rate, you're gonna capture it, what's the free flow speed, and then you're gonna look at what's that level of service associated with these parameters. Any questions for level of service for multi-lane highways or freeways? The last part of this chapter was the level of service for two-lane highways. Yes, that's the one. Two-lane highways are again, were a little bit different in style and even the calculations. I hope, again, you need to watch those couple examples that I put, especially for the calculation. They're very important. I also can ask you, give me 3 to 4 uh, characteristics of a two-lane highway. How can we define a two-lane highway? Those are the key characteristics to define such facility. And then we've gone through now the classification. There are 3 classes when it comes to two-lane highways. Class 1, Class 2, Class 3. I can ask you define for me Class 1. Or what's the difference between Class 2 and Class 3? You should be able to define these as a conceptual question. The procedure is the same, but the base conditions are different. So the base conditions here, again, some of them are similar, which is again having a minimum lane width of 12 feet or a minimum shoulder width of 6 feet, but other stuff here are different. So 0% no passing zone. That's the first time we see it. So you need to be familiar. If I ask you to list for me 4 or 5 different base conditions for two-lane highways, then now the measurements of the level of service. To get the level of service, you need to get to measure the free flow speed or estimate it. So measuring it is going to be using this equation right here, and it's going to be provided to you in the exam. Don't worry. Once you see a weird numbers like 0.00776, this is an empirical equation. Your advisor doesn't remember it, or your professor doesn't remember it, and I'm not expecting you to remember it. So that will be provided. Same thing here. Free flow speed, it can be estimated rather than measured. So it can be estimated using this equation right here. And here we're using BFFS, which is the free flow speed at the base condition, minus FLS minus FA. Again, tables, some of them are similar, like here, same to the multi-lane highways, but some of them are not. The equation here is also a little bit different. Here we have FG times FHV. FG, this is the difference. We have here a grade adjustment factor, table 6.15. We got to know again that why do we have two pieces here of the table? Because depending on the class. If you're doing class 1, you need to enter this table twice. One for the average travel speed ATS calculation, and one time for the percent time spent following calculation. Once that's if it's class 1. So, and then you're gonna pick whether it's level terrain or a rolling terrain. And same here for table 6. You need for 615 and 616. 616, this is FHV calculation. FHV, you need table 616, same thing. Is based off the percent time spent following or ATS. If you're using, if you're doing class 2, for example, all what you care is percent time spent following. If you're doing class A or class 1, you need to do both. If you're doing class 3, it's just gonna be actually the ATS, which is but it's the percentage of the free flow speed. So ATS over the free flow speed. So you would need just to do the ATS. And then these are now the steps to calculate the service measures. Again, this is the equation for ATS. It will be provided to you in the exam, which is the free flow speed minus 0.00776 times VD plus VO minus FNP. And we define what's FNP using the table. This adjustment factor for percentage of no passing zone. So that is table 617 right here. That's part of it. You first, to get to the table, you need to know what's the free flow speed that you calculated or measured previously. Then let's say it was 60 miles per hour. So this is the part that you're gonna enter. And then based on the opposing flow rate, you're gonna get into here, and then you need to know now what's the no passing zone percentage, whether it's 20, less than 20%, 40, 60, and that's how you pick your number. If you are doing class A or class 1, you need also to do the percent time spent following, which is this equation, which is the percent time spent following at the base condition using this equation, plus FNP times VD over VD plus VO. All these equations will be provided to you. Don't worry about them. You just need to know how to use them. And the best way to know how to use them, again, is to look at the example in your textbook, as well as the recorded example that I posted for this facility. So the example that I really want you to understand and follow really well is example 6.6 and 6.7. This is from the fifth edition. The fifth edition, I think it's not recognizing the book, but it's the fifth edition, and it's example 6.6 for the fifth example 6.6 and 6.7. It fully explain the whole concept and how can we use again average travel speed and percent time spent following. And again, A and B here, those are coefficients that you can pick from this table right here. This table we use 618. Really, we we need it for FNP. Please remember that FNP calculations for ATS is different table than FNP for percent time spent following. FNP here, the adjustment factor for passage for the percentage of no passing zone is table 6.18. But if you go a little bit backwards, FNP here, for the sake of ATS calculation, it's table 6.17. So please make the distinguish the difference between the two. Once you get that, again, you'll be good to go for class 1 or 2. For the percent of the for this calculation is only for class 3, which is it's a percent of the free flow speed, which is basically the ATS over FFS. Once you do that, again, now you need to be familiar with this table right here. If it's a class 1, you need to satisfy both conditions. You're gonna go down the list here until you satisfy both conditions to call it good. What to say? Okay, this is the specific level of service. For class 2, you only need percent time spent following. For class 3, you only need ATS over BFFS. I mean FFS. Percent time spent following. I mean the percent of the free flow speed is ATS over FFS. That's what you need right here. So from this chapter again, you will be fine. You will be seeing at least couple calculations, couple calculation problems, as well as maybe 1 or 2 conceptual questions. Any questions on chapter 6? I'm hearing none. So moving forward to last chapter, chapter 7. Sorry. All right, chapter 7 was a first time introduction for traffic control and analysis of signalized intersections. So from this chapter also you will find at least couple calculation questions and couple conceptual questions. I can ask you, please list for me three advantages of having a traffic signal. I give you here one, two, three, six of them. Or I can ask if the traffic signal is designed poorly, or there was maybe no need for a traffic signal. We can see some disadvantages of having traffic signals. List for me three or four. We should be able to tell what are these disadvantages. And then, what's the definition of an intersection versus an approach versus a lane group? Or if I give you a picture like this, I tell you how many intersections can you see? How many lane groups can you see per phase? Or how many approaches do you have? So this picture is one for one intersection. If I draw you another road here, then now we have two intersections, one and two. But if it's just again that picture alone, so I only have one intersection. How many approaches? Again, I have one, two, three, four approaches. If I have an intersection that's five-legged, then it's five approaches. I can ask you now how many lane groups per approach. So approach one, I have two lanes going through, so that's a group by itself. I have a designated right lane, that's a group by itself. I have a designated left turn, that's another group by itself. So I have three groups within approach one versus approach three, for example, or approach four. Approach four, I have one lane that serves through and right lanes, so that's a group by itself, and I have another lane through and right and left turn, so that's two groups. I also need to understand that you understand what are the intervals within each cycle. So I have a change interval, I have a clearance interval, a green interval, all the way to red interval. I can also ask you, what's the difference? What are the types of signal operations? You need to list them for me: pre-timed, semi-actuated, and fully actuated operation. Or I can ask you, what's the difference between a pre-timed versus semi-actuated operation? So you should be able to tell. Or I can give you actually a map for the city of Tyler, and I can point out to you three different intersections, and I'd ask you what kind of operation you should assign there. How can you pick? Based on the definition. So pre-timed is an intersection between two small roadways, two local roadways. If it's a semi-actuated operation, it's an intersection between major road and a local road. If it's a fully actuated operation, it's intersection between two major roadways. This is how we define which operation goes to which intersection. I can also ask you, list for me the three different left turn treatments that we can have. Those are permitted left turns, protected left turns, or compound left turns. Or I can ask you, what's the difference between a permitted left turn and a protected left turn? Then here we're starting now to the calculation part of the chapter. This is here a very conceptual equation that I will not provide to you. This is basically the definition of the saturation flow rate, which is 3,600 seconds over the average headway per vehicle. That's as simple as that. But from there, again, all these equations will be provided to you. The startup lost time, as well as the TN, which is the green time required to move certain amount of vehicles, all the way really to the major equation will be provided to you. Don't worry. It's the capital G, which is the actual green time, plus the capital Y, which is the all red and the yellow time, minus TL. TL is L1 plus L2, last time, the clearance last time, as well as the startup last time. We learned how to get the true capacity of the lane or lane group, which is the SI, the saturation flow rate, which is, again, that's why this is, you need to know, it's 3,600 over H, but then times GI, the effective green time over C. So this equation will be provided. But if you ask me what's SI, you should be able to tell that SI is the same as all the way. This is right here, the saturation flow rate. We have examples. Make sure again to understand those examples. Make sure that you did the homework yourself. If you were able to do the homework yourself and understand the problems that we discussed here, you should be good to go for the exam. We explained the concept of critical lane and the lane budget concept. Very important. And we've went through all the derivation until we reached this important equation. The relationship here emerges that this is the VC, the maximum sum of critical lane volume that we cannot exceed. This is really how we use it to design how many lanes we need per direction. 1 over h times 3600 minus n t n times tl over 3600 over c. I'll be providing you the equation, but you need to understand. I'm not going to define for you what's c, what's n, what's tl. You should be able to understand the definition of each one of the terms. We've gone through the calculations, very important. We also define for us what's the desirable cycle length. That's important. You may see it in the exam as well. If you need it, you don't have to remember it. It will be provided to you. The calculations here are very important. All the way to this problem here. How can we design the C design, the design cycle length by varying the V over C? So having V over C1, which is again, I'm really exhausting the system because now I'm going to use the full capacity. The design cycle length is 65 seconds. But if I use 0.95, 85, which is not bad. 0.9, 130. 85%, now we're being too conservative. That's 290. If you want to do it right, the absolute conservative 0.8, 80% of the capacity, you're going to end up with negative number. What does that mean? That means you can't really design uh, this traffic signal at 80% V over C. And then here they're finding the approach lane cycle length all the way to design. Really, this is a pure design problem. What to define how many lanes per direction are you gonna need. So first, of course, you have to define what's VC. This is the maximum sum of critical lane volume, and then we're gonna assume that we're gonna just put one lane. Always start with the least amount of lanes. This is the most efficient way. So assuming that one lane per direction, so that's 1200 and that's 1800. You're gonna sum them up. V over C now is 3000, way higher than 1357. So that's why we say this not good. And then now you go to the higher bound, which is in this case the east-west bound. You're gonna divide the 1800 into two lanes. Now you have 900 each. Now the new VC is actually 900, which is one of the two lanes, plus 1200. And that's why we ended up with 2100. Still not good because it's higher than 1357. And then now we go now to the next option, which is two lanes north south and two lanes east west. So 900 plus 600, that's 1500. Still a little bit higher than what you need, than what you can afford. Excuse me. Then we go now to the 900. Now we say instead of that 1800 being divided into two lanes, I'm gonna divide it into three lanes, and that's why I have 600 now. So 600 plus 600, that's 1200, less than 1357, which is your maximum sum of critical lane volume, and that you're good to go. We've gone through here a correction. We need to do a correction now for the design cycle length, because now it's not really, you're not using 1357 anymore, you're using 1200. So that's why you're gonna plug it into the equation to adjust the design, the desirable cycle length. Now it's gonna be 80 seconds instead of 60 seconds. And then here we assume the hypothetical problem here, if we are limited by two lanes in each bound, can we really adjust the cycle length to handle that? The answer for this problem was no, because if we really have two lanes in each approach only, which is actually this one right here, and this option right here. So if we have 900 and 600, so 900 and 600 V over C become 1500. So if we go now to the calculation of the desirable cycle length, 1500 now instead of 1200, everything else is the same, you're gonna end up with a negative value, meaning it's not good. So really, you have to have 3 lanes in the east-west bound, and 2 lanes in the north-south bound. So expect something from this chapter. Again, a couple calculation problems from this chapter, as well as maybe 2 or 3 questions conceptual as well. I think that's about it. Any questions on chapter 7? All right. So I guess with that, again, that's all what I have. If you have any last minute question from here till Wednesday, don't hesitate to reach out to me, and we'll see you on Wednesday. Thank you so much, guys.
Thank you.
Thank you.
Thank you.